Let's solve one of the most elegant integrals in mathematics, the Gaussian integral, a result that underpins key concepts in statistical physics, quantum mechanics, signal processing, and many stochastic processes. The challenge is that e to the minus x squared has no elementary antiderivative, so standard calculus techniques do not work. To overcome this, we use a trick. We square the integral, transforming a one-dimensional problem into a volume calculation over the entire two-dimensional plane. This new perspective makes the problem much more manageable, because now we can use its properties to compute this volume by switching to polar coordinates. However, changing coordinates requires care. To transform the surface element dx dy correctly, we must include the Jacobian determinant, which describes how the area is locally stretched, compressed, or distorted by the coordinate transformation. It ensures that integrals remain invariant under a change of variables by accounting for this local scaling of space. When we compute the derivatives, we find that this transformation introduces a crucial factor, r. Now let's visualize what this means. Instead of integrating over a rectangular grid, we are integrating over concentric circles. The extra r factor represents the growing circumference of these circles as the radius increases. This geometric insight is what turns an impossible integral into a solvable one. From here, the calculation becomes straightforward. The variables separate cleanly. The angular part is trivial and integrates to 2 pi. Thanks to the factor r from the Jacobian, the remaining integral matches the derivative of the exponent, allowing us to integrate it directly. Evaluating the limits at 0 and infinity leaves us with a remarkably simple result, which reduces to pi. But remember, this is the value of the integral squared. Taking the square root gives the final and famous result, the square root of pi.